Okay, good morning. Let's have a class. So this is our first microbiology lab. As usual, we will talk about the microscope use. And you can take it out of the cover. If you have a microscope on your desk, then we will talk about those things. Okay? So lab 1 is always microscope use. So we already mentioned in the lecture, microorganism is too small to see. So we need to use a tool which is called a microscope. And the one word we're using here is light microscope. And it is called bright field. So what this means, a bright field light microscope, which means when you have a glass slide underneath the objective lens, then you do the observation, what you will find, the background is bright. And the specimen, which means the sample, is dark. That is called bright field microscope. Okay, so that's the first thing. Second, we want to talk a little bit about the structure of the microscope. So the first question is always, what is the most expensive part of a microscope? It is lens. So we have two kinds of lens. One is on the top. So your eye can go there to see close to your eye. That's called ocular lens. And you have some switch right here. You could be changed to 4x, to 10x, 40x, and 100x. These we call objective lens. Therefore, we come out with our first concept, total magnification. So what is total magnification? It equals the ocular lens magnification multiple objective lens magnification. So give you a very easy example. Ocular lens magnification is always 10x. And the objective magnification, let's say we set at 10x. Okay, multiple. So what's the answer? It is 100x. If the objective lens, the magnification we set at 40x, what will be the answer? 10 multiplied by 40 equals 400x. If the objective lens magnification is 100x, what will be the answer? 10 multiplied by 100 is 1000x. So that's the first thing first, is total magnification. Okay. Second thing what we want to talk is working distance. So what is working distance means, we may have to move to in the middle stage right here. And I said the most important parts of a microscope is the lens. So we will talk about the objective lens. If you notice the objective lens, there is a form. The one what we use in the lab, which is 4x, 10x, 40x and 100x. And underneath the objective lens, there is a stage. The stage we call, it is a specimen control place. We could put a glass slides there, then do the observation. So right here, okay, glass slides can put it there. We do the observation. So what is the working distance? So working distance is the distance between the stage to the objective lens. And you will see the working distance is decreased with the increasing of the magnification of an objective lens. So what is the working distance? Distance between objective lens to stage. And the distance is decreased with increasing of magnification of objective lens. And you can see it. So here comes with a problem. What is the problem? Underneath the stage, there is a light resource. And we talk about light microscope, which means the energy is light. So the light is right here, there is a condenser, and there is something called control the light amount, we call it an iris diagram. So the light going through from the bottom of the stage, first they're going to go to the air, and then they go to the objective lens. So let's say there's a light right here, okay? Right here, right here, right here. So what they do? They go up. That's not a problem. From the bottom, go through condenser, and go into the stage. Now they're causing a problem. Because the light resource and the condenser is glass. This section is glass. This whole section. And here is air. Remember? If light going through one medium to another medium, they will cause a very interesting and normal physical phenomenon, which is called a refraction. Is that right? So that means some will going through the objective lens, some will be refracted because it's going through a different medium. And we also know that there is an index called refraction index, or I, to tell us the number of the reflection effects. And the refraction index of glass is 1.5, and the refraction index of air is 1.0. So what happened? Somehow refracted will make it looks very fuzzy. It's not going to be focused the light. This is obviously when you using a microscope. For example, use 4x, you find a sample. Then you turn to 10x, you find a little bit large, but it's unclear. Then you go to 40x, it's more unclear. When you go to 100x, it's completely fuzzy because the refraction is enlarged. So how to solve this problem? We know that find something could remove this air gap. What is that? A one drop of big oil. Therefore, we comes out with a Third concept is oil immersion. What's the function of the oil immersion? Is remove air gap, minimize light refraction effect. So how we do it? We usually add 1 drop of the oil right here. A big drop has to cover the objective lens. That's called oil immersion. Now, why we use oil? We do not use other material because the refraction index of oil also equals 1.5. These two are the same. It's the same refraction index of oil and glass. Therefore, they remove the air gap. Therefore, underneath the microscope, we usually use 10x to find the specimen. Then we switch to 100x. We add 1 drop of the oil. They looks like they connected. And then we can see the morphology, which means the shape of the bacteria. Okay, so that is a story. So number 3, which is we call it the oil immersion. Okay, number 4. It's called a parfocal. So what it means parfocal? You have 4 different lens, objective lens. 40x, 4x, 10x, 40x, and 100x. If we are using 10x, we find the specimen already. And we find it, but we cannot see it very clearly. Then we put 1 drop of the oil, then we switch to 100x. It will stay focused, and we only need to do a little adjustment. Where are they? Well, what do we do? These are called focus control. The SICK knob is coarse focus. That used for 10x focusing. And the thin one, the thin knob, which is the fine focus. Which means you use SICK knob to do the coarse focus. You already focused at 10x. Then you switch to 100x. Let's say 10x you already focused. Then you switch to 100x. You only need using a fine knob to do a very tiny adjustment, and it stays focused. So, what means a parfocal? Once focused, lens stay focused. Only need minimal adjustment. So that means switch from 10x to 100x. Only need a very tiny minimal adjustment. This is a very good characteristics of a light field microscope. Because otherwise you have to, from the beginning, to redo everything. It takes lots of energy and time to do it. Imagine if you have 100 slides, you have to do the observation, you have to write a report. That's gonna make you took lots of time to do. Okay, so parfocal is a very good characteristics for the light field microscope. Last thing what we want to talk is called resolution power. Resolution power has a formula to do the calculation. Is RP equals lambda divided by 2 multiple NA. So we want to talk about these index. First of all, what is lambda? Lambda is a light wavelength. The microscope, what we are using here, if we turn it on, plug in, turn it on, and switch the electricity to the largest side. So let's say turn it on to the largest side. This light wavelength is equal 625 nanometer. So that is lambda. 625 nanometer. What is Na? Na called numerical aperture. And I always say the numerical aperture, it is like a size of the engine. Like a size of the engine of the car. It is the size of the engine of a microscope. How do we find that number? If you look at 100x objective lens, you will see their writings here is OU 1.25. This number is numerical aperture. So this microscope, if we use 100x with OU immersion, this numerical aperture number is 1.25. So we could do a very simple math calculation. So this is 1.25. So what it equals? 625 divided by 2 multiplied by 1.25 equals 625 divided by 2.5. That equals how much? 260 nanometer. Can we do a very simple unit conversion? 260 nanometer is equals 0.26 micrometer. So remember, 1 micrometer equals 1,000 nanometer. And this number is very important here. So I want to explain to you why. Can you guess an average size of a bacteria? How large it is? Let's say I have a bacteria which is Staphylococcus aureus. What is the size around? It is very small, 0.5 micrometer. So can we use light field microscope to do the observation of Staphylococcus aureus? Yes, we can. Why? Because our resolution power 0.26 micrometer is less than that. The resolution power equals 0.26 micrometer is less than 0.5 micrometer, the size of Staphylococcus aureus. So we can use light field microscope to do the observation. So I have another question for you. How about a virus? Let's say a HIV virus. What is the average size of a HIV virus? It will be only 10 nanometer. What is that? 0.01 micrometer. Can we use light field microscope to do the observation of virus? No, we cannot do it because the resolution power 0.26 is larger than 0.01 micrometer. So we cannot do it. Therefore, due to observation of virus, we need to rely on electron microscope. Is that right? We talk about this in the lecture. So here, which means the resolution power should be the smaller the better, because small resolution power indicate big resolution capability. I should say small resolution power value indicate big resolution capability. Okay? So these are the terminology we want to explain to you before we using the microscope, which is total magnification, working distance, oil